Multi-protocol label switching, MPLS. So we are going to see MPLS part 1, and then we need to go to BGP, learn BGP properly, thoroughly. Then we'll come back to MPLS part 2. So today our focus is to finish part 1 of MPLS, and if time permits, the second session we will have BGP. Multi-protocol label switching. As we saw in the previous class, this is reducing the time taken and the process that is taken to route a packet. Ceph quickens the routing decision by keeping the layer 3 information in a layer 2 buffer called Cisco Express forwarding or forwarding information base. That helps avoiding layer 3 route lookup on the router. So the router's engine, the router's layer 3 chipsets are not frequently used because the necessary layer 3 informations are received in layer 2 level itself, and there is no need for layer 3 lookup. In that way, Ceph quickens the routing decision. Ceph is the one which maintains the routing informations in layer 2 level. Now, what MPLS does is MPLS layer gets added to the OSI reference model 2.5, meaning after layer 2 and before layer 3, you will find another layer in between layer 2 and layer 3. We call it as MPLS layer. After data link layer and before physical layer, before network layer, you will find MPLS layer. And the information in the MPLS layer will inform the processing router, the router that processes this packet will be informed about the destination so that there is no need for the network layer to get processed. There is no need for network layer. There is no need for the fields in the network layer to be processed. The receiving router, when there is no MPLS, it has to process that big layer 3 header. After processing the big layer 3 header, it will know the destination. The routers will know the destination. But now, after MPLS, there is no need to look into layer 3 because the destination is already known to the router that is processing the packet from this MPLS header, the MPLS layer. Because it is between layer 2 and layer 3, you can call it as layer 2.5. MPLS layer is in layer 2.5. How MPLS provides destination. not in the form of IP address, but in the form of a label that is mapped to an IP address. So when you enable MPLS, IPs are not involved in packet forwarding. Instead, the labels are going to be used. So labels replaces IP. Is it true? Yes, it is. When we enable MPLS on routers in the path, those routers are deciding the destination and the next hop to reach the destination based on the labels that is carried in the packet. See, this is not only a foundation for MPLS, this is also a foundation for segment routing. Segment routing will also have a similar approach, but quite advanced than this. Without MPLS, segment routing is not possible in IPv4. In IPv6, you can have segment routing with MPLS, even without MPLS. Whereas in IPv4, you depend on MPLS for segment routing. So whatever we learn here is very important for even the following topics. What we learn here, we have a label which is going to be the reason for routing. Because the labels are used here, we don't use the word routing, instead we say label switching. Label switching. So multi-protocol label switching avoids scanning this big network layer header. See, in the network layer, we are not only having source and destination IP address. We got fragment field, offset field, option field, TOS field, version, protocol, much more, TTL. Lot of fields are there in layer 2. But you may not be interested in knowing all those informations in that layer 3 header. You need only the destination where to forward the packet. When I say you, I mean the routers. The routers in the path, all they need to know is the destination to where the packet needs to be forwarded. But in order to know the destination, every router needs to read the complete layer 3 header. Complete layer 3 header need to be scanned. Only then the routers will know where to forward. But MPLS does what? MPLS only have necessary information, not too many fields, and that too, the destination is identified with a label which is very small than an IP address. So the time taken and the process taken to forward the packet will not be much. Size of the IP header will be very big depending on type of packet. It will be in thousands. Whereas the MPLS header is only 32 bits, just 32 bits. The total size of MPLS header is 32 bit. What about the size of IP address, source and destination in network layer? What is the size of IP address in the network layer? What is the size? I think you are in mute. What is the size of IP address in network layer? 32-bit. IP address size is 32-bit. So source is 32-bit. Destination is another 32-bit. So just the IP address itself is 64-bit. But you see the MPLS layer, the total size of the MPLS header itself is only 32-bit. The routers in the middle, they don't want your source. They need only the destination to where the packet need to be forwarded. MPLS is going to have a label which is pointing towards the destination. And the total size of MPLS header is only 32 bits. Just 32 bits MPLS header, which is the size of one IP address, right? But with this 32 bit, what all it can do, it can identify the destination to where the packet needs to be forwarded. That's number one. Number two, it identifies the quality of service or traffic engineering needed for the traffic. Second, third, it identifies the TTL for the packet. So just 32-bit can provide these many informations. Again, these three informations are more than sufficient for a packet to be routed. This three information is what a router needs to know with respect to a packet that is getting routed. What is TTL? Okay, what it is? And where do we see TTL? In a packet, where do you see TTL? Fine. If you see layer 3 header, you will find a field called time to leave, TTL. Now, when I enable MPLS, we are not going to look into layer 3 header, which means we are not going to look into the TTL. But TTL is very important. That is why MPLS also copies the TTL from layer 3. Listen, in layer 3, we have a wonderful loop prevention feature called time to leave, TTL. How TTL is loop prevention? TTL will be decremented by 1 as the packet jumps every hop. You know what is the default TTL value when a computer sends a packet? That depends on the operating system. If you are using Linux operating system, when a packet is sent, the packet will be sent with TTL of 64. Only 64. So the packet can go only 64 hops. If you are using Windows, the default TTL value will be 128. Okay, 128. And if you take Cisco devices, the default TTL value will be 255. So TTL value is not same for every operating system. It varies. Yeah. I'm sorry. Okay. Other vendor router. Mostly routers will have 255. That's as per the standard. But operating system, uh, some 64, some 128. But routers I have seen 255. But again, we cannot guarantee. Sometimes there may be less than 255, but cannot be more than 255. Why? Because the number of bits that are allocated for TTL is only 3 bit according to the OSI standard. Yeah. Here we go. MPLS is only 32 bit, but it can provide all these informations. The time to live in layer 3, we are not ignoring it because it's important. So the time to live is copied down to MPLS header. For every hop, the TTL is going to be decremented by 1. Say for example, I'll go to command prompt and type ping www.yahoo.com. I can see the TTL of 53. See, this is a packet coming as a reply. If I'm getting a reply packet as 53 TTL, which means, okay, here it is 54, which means 10 hop away. You see, this is a Linux server, I can understand. Linux servers will respond with TTL of 64. So when it started from there, it was 64, and every hop it got decremented by 1. And when it reached me, it is 53, which means 10 hops away. Yahoo is 10 hop away from me. Can you ping and see how many hop it shows for you? Take your time. Did you get? Just try pinging www.yahoo.com in your command prompt and see the TTL that you get. Okay, so it is coming via different routes. That's why you got multiple routes to come in. Okay, so if it is 35, then 64 minus 35. let's take 40 as an average. So you got like 24 hops away. Yeah, for you, Yahoo server is a bit far away from my location. See, Yahoo has got a different mirror copy in various places. So my IP address, if you see here, it is 107.50. What is yours? No, IP address. When you ping, what is the IP address it shows? MAC address? It may not be MAC address then. It may be a link local address. IPv6. Can you take a screenshot and send it to me? Yeah. Okay, so this is what you get. This is IPv6 address actually. Very nice to see. You are in UK, right? Germany. So it's IPv6. It's IPv6 and TTL is 40. TTL is 39 or 40. Let's take average of 40. Calculator. No, calculator. I mean calculator. 64 minus, let's say 40. 24 hops away. Yeah, 24 hops away. For me, just 10 hop away. Wonderful. So now let's go back. That's TTL. Time to live is very important. If somewhere loop happens, the packet will be valid only till the TTL becomes 0, and then it will disappear. In that way, you avoid loop. Time to live is a loop prevention mechanism in layer 3. You don't need to enable this loop prevention mechanism. It is there by default. If some reason loop occurs, that loop won't prevail for a long time. It won't continue for a long time. It will just go for like 25 or 48 or 128 hops, and then the packet will disappear. It depends on the operating system. And when I enable MPLS, I'm not compromising on that loop prevention mechanism. I'm going to have the same TTL value copied into MPLS header so that you will still have the TTL loop prevention mechanism in MPLS. So what MPLS provides is the destination, the QoS, and the TTL in just 32-bit. Now, if I take IPv4 header, for destination there is 32-bit. For QoS there is like 6-bit. And then for TTL there is 8-bit. Just for this three thing itself, it is 46 bits. But you will not just read this 46 bit. The network layer is of thousands of bits because many fields are there: option field, fragment field, protocol field, version field, checksum field, fragment field, yeah, sequence, many more. Whereas MPLS totally is 32, but it can provide all the necessary information which is needed for a packet to get routed. Destination, QoS are TE bits, which will provide you the quality of service or traffic engineering bit, and then the time to leave. So definitely MPLS is very good than a normal routing. it is going to be faster. Now let's quickly see the header, how it looks like, the MPLS header. As I said, MPLS header, the total size is only 32. In that 32, first 20 bit is for label. First 20 bit. That what is the size of the biggest label? The maximum label that you can have is 2 to the power of 20. Oh, that is going to be a very big number. In a router, you will not have that many thousands of routes. 2 to the power of 20, it's really a big number, some millions. Followed by 3 bit. We call it as COS bit or traffic engineering bit. It is also called as experimental bit. So 3 bit, you can use it as COS, class of service, or it can be used by traffic engineering. Yep, class of service. Because this is not a layer 3, you have layer 2 terminology. In layer 2, QoS is called as COS. The same term is also given for QoS and MPLS. COS bit. So you can use that 3 bit as a COS bit or traffic engineering bit or for some other purpose. That is why they call it as experimental bit. Experimental bit. The 3 bit is called as experimental bit because it can be used for any other purpose also. Now next is we got 1 bit, just 1 bit as bottom of a stack. What is bottom of a stack? The stack we know, keeping one above the other. See, this is one box, and to save some place, instead of keeping another box here, we keep it over here. Another box over here. You might have seen in some older houses. We keep one box over the other to save some place. Or the bricks, yeah. The bricks are kept in stack, one above the other. Even the chairs, chairs, we keep one inside the other so that it will not take much space. When no one is there to sit, we stack it. This is what called a stacking. Yeah, yeah, it is stacking. We keep one switch over the other, stacking. Now, if you see the rack, you will know which one is the bottom switch because we can see through eyes. Even here, I have drawn 3 boxes, and you will tell this is the bottom of the box, and this is top, and this is middle. But routers don't have eyes. For routers, we use this bit to say this is the bottom of the MPLS layer. See, we can have more than one MPLS layer in a packet. Listen, please. We may have more than one MPLS layer for a packet. Why? One is for the local switching, the other one is for the VPN. We'll be learning these things in detail a bit later. But what I'm coming to say is if you have VPN with MPLS, definitely we'll have more than one layer of MPLS. When we have more than one layer of MPLS, how the processing router, how the router that processes the packet knows that this is the last layer. If this bit is on, if the bottom of a stack bit is on, see these are all off. 0 means off. If the bottom of a stack bit, if this one bit is on, then the router knows that I'm processing the last MPLS header. You understand? So when a router is receiving packet, it will start processing MPLS header, but how router knows that I'm processing the last header or the first header or the top header? From this bit. If this bit is seen 0, then there is one more layer to process. If it is 1, then this is the last MPLS layer. I can take decision. I no need to process another layer of MPLS. So for that you have bottom of a stack bit. At last we have 7 bits. 7 plus 1, 8 bits, which is called as time to leave bits, TTL bits, time to leave bits. So the 32-bit MPLS is divided into these 4 small sections. 20 bit is for the label, 3 bit is for the sake of QoS or traffic engineering, and then 1 bit is for telling whether this packet is the last MPLS header. This header that we are processing is the last MPLS header or not. If the bit is 1, then this is the last header. If the bit is 0, then it is not. And then the time to leave, which is copied from the IP layer to this MPLS layer. Okay, so now 32-bit, 20 plus 3 plus 1 plus 8, 32-bit. This is how it is. Next, when a router receives a packet from IP, see this is not MPLS, this is IP. MPLS is starting here. Let's say from the customer the packet is coming without any MPLS. So MPLS is getting added here. When the packet goes out, it goes out with MPLS header. We call this place as ingress router, or the router where label impose, means label is pushed, push operation, push.
That is PE, you call.
Yeah, you can also call this provider edge router. This is the router where the labels are imposed to the packet. Label push operation happens, push operation. So what happens, when it pushes the label, For example, if the packet is coming with TTL of 50 in the IP header, that 50 will be reduced to 49 now when it hits here, and that 49 will be copied to the MPLS header, and when MPLS header goes out, it goes with 49 TTL. This is MPLS header, this is IP header. So what I'm coming to say is the TTL of the network layer is copied to the MPLS layer in the PE router. Adding of MPLS header is called as label impose or push operation. Push operation. Push operation is done on the ingress router. Pop operation, pop. Operation popping means what? Removing the label from the packet so that when you send it to the customer, you will send it with simple IP packet. Because the customers don't run what? They don't run MPLS. So when we send the packet to the customer, we pop the label out or label dispose. Here it is impose, here it is dispose. Label dispose happens, which is also called as pop operation. And now when it dispose, the TTL is copied back to IP layer. See here, MPLS header 49, MPLS header 48, MPLS header 47, and when it is pushing out as an IP packet, the 47 will be copied to layer 3 header and send it to the customer, and customer will reduce it to 46. So what do you understand from here? The TTL is still maintained. Even after enabling MPLS, the TTL is maintained. If customer is sending with 50, when it goes out, you see it goes out with 46, which means in the middle, the TTL is getting decremented for every hops. But the difference is that decrementation happened in the MPLS header here, and it got copied to the network layer. Yep. Okay. So label impose or push operation, pop operation. There is also one more called swap. Swap. Swapping is nothing but changing the label for every hop. That is what swapping. Swapping the label. Now, before we go to swap and all, we have to learn some more concepts. Then we will come back to this push, pop, and swap. As I said, MPLS is 32-bit. Push operation happens in the ingress PE router. Swap operation happens on every router in the middle, and pop operation happens on the egress router. Now for swapping the label need to be distributed. When we enable MPLS, a protocol called LDP gets enabled automatically. What does LDP stands for? Label Distribution Protocol. It uses TCP 646.